Hello and welcome students. This is lecture number 14 on derivatives. We are right now in derivative of logarithmic functions. So we will continue with the same. Let us solve few more problems on derivative of logarithmic function. So here we have a question, differentiate with respect to x. And what is the function to be differentiated? It is this function that we want to differentiate. Okay. The function we have here is x raised to x raised to x. Okay, so remember the bracket is not given. Listen here, the bracket here is not given. Remember, whenever you have power of power of power and the bracket is not given, it is always to be considered this way. See, it is x raised to x raised to x. It is this way. Okay, and here also it is e raised to x raised to x. It is this way. What I'm trying to tell you is never ever, suppose you have p raised to q raised to r and the brackets are not given, so you will take it this way. It will be p raised to q raised to r. Okay, this is how you will take it. Don't take it p raised to q raised to r, and if they do not give the bracket, so don't take it this way. Okay, don't take it this way. If you go this way, then it is wrong. If the brackets are not given, then it has to be this way. And if at all if they mean it to be this way, then they will give the bracket. I hope I have made it clear what is it. So here what we have is we have x raised to x raised to x plus e raised to x raised to x. Okay, so as usual, the first step will be here. Let y equals to x raised to x raised to x, and I have a bracket here, plus e raised to x raised to x, I have a bracket here. Now in last lecture I explained you that whenever you see variable raised to variable, then having a log is mandatory. Taking a log becomes mandatory, because without log you cannot go ahead. It is not possible for you to get the derivative without taking log. So see here, I notice that it is variable raised to variable. So what I will do, I will take log on both sides. I will take log on both sides. Okay, but then once again I notice a big trouble here. What is that trouble? That we got a plus sign here. Now you know, if I take log on both sides, if I take log on both sides, I will get log of y equals to log of this 2. Okay, now log of this 2 will be in the form log of m plus n, and which is not done. It is not allowed. Okay, not allowed means if I have log of m plus n, I will not get my purpose solved. My purpose is to get log of m, to get log of n, which I will not get if I'm having log of m plus n. And I have explained this in much detail in last lecture. So in the previous video you can get the solution of this. So this is this is y equals to excuse me. So y equals to x raised to x raised to x plus e raised to x raised to x. So what is the method here? I write this as, I write let u equals to, I will take this as u. The first one I take it as u equals to x raised to x raised to x. Okay, and v equals to e raised to x raised to x. So what will happen? I will get y equals to u. I will get y equals to u plus v. This is my equation number 1. I write here differentiating with respect to x. Definitely, if you take this as y and this as v, y will become u plus v. Now, when you differentiate both sides with respect to, x, what do you get? You get here, you will get here, therefore, d by dx of y equals to d by dx of u plus v. Okay, that is dy by dx equals to d by dx of u plus d by dx of v, plus d by dx of v. And what happens now is, this is equation number 2. This is equation number 2. What I will do next is, now I have understood that to get du by dx, I will take this and differentiate. See, I now have to find du by dx and dv by dx. Once I have got those two, I will differentiate, I will add them both and I will get the required dy by dx. So I will write here, consider u equals to x raised to x. I take log on both sides. So here I write taking log on both sides. Now I take log on both sides. I'll get log of u equals to log of x raised to x. And you know what is log of m plus n. So, sorry, log of m raised to n. You know what is log of m raised to n. This is m and here you have n. So log of m raised to n will be n log m. So what do you get? You get x raised to x into log of x. This is what you get. X raised to x into log of x. Now here something very interesting is happening. See, something very interesting we are coming across. And what is it? See, I noticed that even after taking log and having this x raised to x as a coefficient, okay, so we got rid of this variable as a power of this variable, but still, see, we don't have, we got rid of this x raised to x from the power part. Okay, it is no more in the power part here. Okay, it is no more in the exponent here. It has come here. See, you can check here. But still I notice that I have that variable raised to variable thing. See, x raised to x. I still have that x raised to x. Okay, so since I still have x raised to x, what I will have to do? I will have to take log once again. I will take log once more. So here I write taking log on both sides. Taking log on both sides. And this step is quite important. You know, this step, normally students don't realize this. This step is very important. What we are taking log for the second time. So when you take log on both sides, so what do you get? You get log of log u equals to log of x raised to x into log x. Log of x raised to x into log x. And now what it is? It is log of m into n. You see this? When you took log for RHS, you get log of this. So, and that is in the form log of mn. It is in the form log of mn. So what is log of mn? Log of mn is log m plus log n. Okay. So you get therefore log of log u equals to log of m, that is log of x raised to x. You get log of m, that is log of x raised to x, plus log of n, log of log x. Okay, so this will now you will get finally something where you will have no variable raised to variable. See, you have log x raised to x, you have log x raised to x, so this x will come down here. So what it will get you? It will now get you log of log u equals to x log x plus log of log x. This is what you get. And now this is the step where you can start differentiating. Here you will start differentiating. And when you differentiate with respect to x, you will end up getting du by dx. So you will write differentiating with respect to x. So here you have therefore d by dx of log of log u, d by dx of log u equals to d by dx of RHS. In RHS, you have x log x plus log x. In RHS, you have x log x plus log x. Okay, so here, now we will go for the derivative. So here we have d by dx of log u. This function is, every time, as you know, when you want to differentiate, you will have to recognize the function. This function is log function, but what I notice is, though it is a log function, it is not log of x. It is not log of x. It is composite function. The variable of this log function is log u, and you are differentiating with respect to x. So the variable isn't matching here. You understand? The variable is not matching. So I will go for derivative, and derivative of log u with respect to x will be 1 upon log u into d by dx of log u into d by dx of log u. See, I could have directly written, I'm telling you, d by dx of log u, we should be writing directly. What I should have written, I should have written d by dx of log u as 1 upon u d by dx of u. I'm not writing, you know the reason. The reason is I'm writing all the steps so that any student, if she is doing, they should not find it difficult. But I would suggest you that all such small steps you shouldn't be writing. You can always skip these steps. See, here what I did, I wrote d by dx of this and d by dx of this. You could easily skip this also. You can directly write the derivative. So here you will have 1 upon log u, and check here what you have. You have here d by dx of log u. D by dx of log u will be 1 upon u d by dx of u. And here we have x multiplied to log x. So product rule. X derivative of log x, 1 upon x, plus log x derivative of x, 1. Plus this is d by dx of log x. So 1 upon log x into d by dx of log x, which is 1 upon x. Now here I notice that this x and x cancels, these two x cancel here. So the next step I get therefore, now see, I get here 1 upon log u into u, that is u log u into du by dx equals to, this is 1 plus log x plus 1 upon x log x. Okay, so finally we want du by dx. So what will be du by dx? Du by dx will be this u into log u. I will shift it on the right hand side, it will go in numerator. So u log u, and inside the bracket 1 plus log of x plus 1 upon x log of x. Okay, this is du by dx. What is the next step? The next step is, now I will substitute for u. What u was? U was x raised to x raised to x, x raised to x raised to x. So here I'll write, I get therefore du by dx, d by dx of u is, for u we write, what we write? We write x raised to x raised to x, x raised to x raised to x. Okay, and then we have log of u. For log of u, see, you have got the value of log of u also. What is log of u? Log of u is, you can directly write from here log of u. See, log of u. Log of u is x raised to x into log x. So you can directly write from here. And even if you do not write, you simply write, see, if I substitute for u only, then also it will become the same thing. How? See, log, and what is u? Yeah, if I write for u, u is x raised to x raised to x. So anyways, this x raised to x will come here because log of m raised to n. Okay, so this, and then you have inside the bracket, what do you have inside the bracket? You have 1 plus log of x plus 1 upon x log of x, 1 upon x log of x. This is du by dx which you got. So you have du by dx as x raised to x raised to x into x raised to x into log of x, 1 plus log of x plus 1 upon x log of x. This is number 3. Now what we will do? We will go for v. See, we will go for v. What is v? V is e raised to x raised to x. So I write now, consider, I'll write here, consider v equals to e raised to x raised to x. Again, see, here I have e raised to x raised to x. Okay, as I told you that you will have e here. Now, see, I take log on both sides. First time I take log on both sides, I write taking log on both sides. Taking log on both sides. So when I take log on both sides, I get log of v equals to log of e raised to x. This x raised to x will become the coefficient. It will become the coefficient. So log of v equals to x raised to x log e. And what I know that log e value is 1 because the base is also e. So next step I'll get therefore log v equals to I'll get x raised to x only. Okay, so I have taken log once. Because of which this x raised to x has become the coefficient. But I notice that I'm still not over with that variable raised to variable. That variable raised to variable is still there. See, it is x raised to x. So what I'll do, I'll take log once again. So I write here, this time we will get that what we want. So I write here taking log on both sides. So I get log of log v equals to log of x raised to x. Again, I'm suggesting that you could write it directly. Log of x raised to x. Instead of that, you can write x log x directly. So, but then make sure that when you are writing directly, make sure that you are knowing it. Okay. You should not be doing it deliberately. So x into log x. And here I will write differentiating both sides with respect to x. So I write here differentiating with respect to x. So d by dx of log v equals to d by dx of log v equals to d by dx of x log x into log x into log of x. So derivative of d by dx of log v, it will become 1 upon log v into d by dx of log v. And here I have x log x. So I will use product rule x d by dx of log x plus log x into d by dx of x. So what will this become now? It will now become therefore 1 upon log v d by dx of log v is 1 upon v d by dx of v equals to x into 1 upon x d by dx of log x plus log of x into 1. So next step, therefore you get dv by dx or d by dx of v, dv by dx equals to, see this v log v will multiply in the numerator. So you have v log v, in bracket you have 1 plus log x. You have 1 plus log x. Now we substitute for v. What is v? V is e raised to x and log v is x raised to x. Log v is x raised to x. So here I write therefore I'm using this log v here. Log v is x raised to x. And this is 1 plus log of x. This is number 4. This is number 4. So now I can write using 3 and 4 in equation 2. So this is equation 2. And when you do that, you get the final answer. What do you get? Therefore, you get dy by dx equals to x raised to x into x raised to x upon into x raised to x into log x into log x, and inside the bracket you have 1 plus log x log x. 1 plus log x plus 1 upon x log x, and then dv by dx. What it is? E raised to x into x raised to x 1 plus log x. This is your final answer. This is the final answer. Now see, there are some more easier questions after solving these big questions. Some of the easy questions you can solve on your own. See here, we got a function where we have the sum of four functions. So what would be the first step? If I want to differentiate this with respect to x, I will first write y equals to x raised to e plus x raised to x plus e raised to x plus e raised to e. Now see here, we have just one variable raised to variable. Remember students, if I did not have this, if this wasn't there, check. If this was not there, then I would not need taking log on both sides. See, if I did not have that x raised to x, you see this, if I did not have x raised to x, then I would not need log on both sides. Why? Because then I have, see, this is variable raised to constant. This is variable raised to constant. Derivative of this will be e raised to e into x raised to e minus 1. Because it is of what type? X raised to n type. So its derivative would be e x raised to e minus 1. This is e raised to x. The derivative would be simply e raised to x. And this is e raised to e, which is a constant. So its derivative will be 0. So this is what I would get if I did not have that x raised to x, which was here in the middle. Okay. Now what is happening is, just because of that x raised to x, the whole process of derivative will change. The whole idea will change now. Why? Because now you understand that you cannot differentiate this unless you have this x down here, and that can be done only by taking log. Further, I cannot take log on both sides because I have got plus sign in between. So what I would do, the idea is I will write here, see, what I can do is I will write this one as u, v, w, and z. So I can write here u equals to x raised to e, v equals to x raised to x, w equals to e raised to x, and z equals to e raised to e. So y will become u plus v plus w plus z. So dy by dx will be du by dx plus dv by dx plus dw by dx plus dz by dx. And then you can solve this separately and then add them all. Okay. This is for you to write the answer if you are getting this question in your, say, board exam. But suppose these questions you get for some CET exam, then what would you do? See, for CET exam, I will tell you that remember d by dx of x raised to x now. Okay, it is time that we remember d by dx of x raised to x. So if I say I have u equals to x raised to x, so what will be log of u? Log of u will be log of this, that is x log x, and then what will be derivative if I differentiate on both sides? This side I will get if I'm differentiating both sides with respect to x. So this side I will get what? D by dx of log u, that is 1 upon u into d by dx of u. And here what I will get? Product rule, d by dx of x log x. X derivative of log x plus log of x derivative of x. Now this x cancels. So what I get? I get du by dx equals to u multiplied to 1 plus log x. Okay, and what is u? U is x raised to x. So you can substitute for u. So when you do that, what do you get? You get therefore d by dx of x raised to x is x raised to x into 1 plus log x. So what I suggest you is, now it is time you learn this, and commit this to your memory. Okay, this one is to be now learned by heart. What is d by dx of x raised to x? D by dx of x raised to x is x raised to x into 1 plus log x. So I can write the answer of this in one step. See what I will write. Dy by dx for this will be e raised x raised to e. This is variable raised to constant. So it is x raised to n type and the variable is x only. So it is a standard function, direct function of x. So e x raised to e minus 1 plus x raised to x derivative is x raised to x 1 plus log x plus e raised to x plus 0. This is your final answer. This is the final answer. This you can do in one step. Okay. So what I said, it is time you remembered this. You remembered this. Fine. Very good. Now I take the next question. This is sub question 7 from the same exercise and same second question. Here I have to differentiate. You can check 10 raised to x raised to x plus x raised to x raised to 10 plus x raised to 10 raised to x. Okay, so what I will do, I will, as usual, the first step is always we will consider this all to be y. Then now I write this as u. This is u, this is v, this is w. Nothing going. That is what you will do. You will write this as u. So u equals to 10 raised to x raised to x. Then you will take log on both sides. So you'll get log of u equals to log of this log of 10 raised to x raised to x. So that is x raised to x log 10. X raised to x log 10. You will get log of u. Next, what you will do, you will take log once again. Why you take log once again? Because you still have that variable raised to variable. So you will have log of log u equals to log of this whole thing, log of x raised to x into log 10. So this will be log x raised to x plus log 10. And log x raised to x will be x log x, and then you can solve. Same thing you will do here. This one you will take it as v. So when you take that as v, you will have v equals to x raised to x raised to 10. So you take log on both sides, log of v equals to x raised to x raised to x raised to 10. Okay. Then what? Log of v equals to, you got x raised to 10 into log x. X raised to 10 into log x. So as such, in this case, you don't have to take log once again. See how we took log here once again. Why did we take log once again here? Because here we had x raised to x, but that, and which is variable raised to variable type. Okay, but that is not happening here. Here we have variable raised to constant, so we don't need a log for differentiating this. So we can differentiate this, and that will be by product rule. So when I differentiate this, so I will have d by dx of log v, which is 1 upon v into d by dx of v, and here this is product rule. X raised to 10, derivative of log x is 1 upon x, plus log of x, and derivative of x raised to 10 is 10 into x raised to 9, and you can solve this. Same way you can try this also, and then you will add all the derivatives, because that is what you are going to, you will add all the derivatives. So that will be, this is u, so this is u, this is v, this is w. So y is u plus v plus w. dy by dx will be du by dx plus dv by dx plus dw by dx. So after having found those three, you substitute in the required equation, you will get the final answer. So you can solve this also. With the last lecture, we have completed the derivative of logarithmic functions. Now we are starting with derivative of implicit functions. We have to learn derivative of implicit functions. So before I do that, let me first teach you what is implicit functions. See, the functions can be broadly classified as functions. Functions can be broadly classified into two. One is explicit function. One is explicit function, explicit functions, and the another is implicit functions. Now, how do you know that which one is an implicit function and which is explicit function? So for that, now I give you the complete detailed definition. So here now I will define both the functions for you. So let me begin with the definition of explicit function. See, if x and y, if, let me use the white color. If x and y are real variables, what does that mean? It means they are variables and they assume only real values, real numbers. So if x and y are real variables, such that a function f is defined, a function f is defined on x, a function f is defined on x and y equal to f of x. A function f is defined. X and y are two real variables. What are x and y? They are real variables. Such that you can define a function on x. Okay, that is, x is independent variable and y is dependent variable. You can define the function on x and you can write y equals to f of x and y equals to f of x. Then f is said to be an explicit function. It is said to be an explicit function. Explicit function. I'm sorry. It is said to be an explicit function. So, what is important in explicit function? In explicit function, it is important that you will always be writing the function in the form y equal to f of x. You will always be writing the function in the form y equal to f of x. Every single time you notice that a function is defined on x and you are writing, you can write it in the form y equal to f of x. You call that function as an explicit function of x. Okay, what is that called as? That is called as explicit function of x. In short, you will notice that you have got only x in the expression where the function is defined and y is on the other side. Y is on the other side. X and y, they are on two different sides. You are writing y equal to f of x, or in more simple terms, you can say that you are able to express y in terms of x. That is y is expressed in terms of x. In such functions, what happens? Y is expressed in terms of x. So here I write, in such functions, y is expressed in terms of x. Okay, that is one side you have y and other side you have function of x. So now you can say that we had been solving all problems till now were in this form only. All the problems that you have been solving, all the functions that you had been differentiating until recently, they all were of this type only. Yes, you are perfectly right. See, everywhere, all the problems that you differentiate, see here also what you have y equal to f of x. See, you have in the form y equal to f of x. Y on the left hand side, see y on the left hand side here, and on the right hand side what you have in everything in x. So such function is known as explicit function of x. This is also explicit function of x. And two more examples here I had given. See here, even in this case, here what you have y expressed in terms of x. See, y on the left hand side equal to everything in x here. So what you notice is on other side, that is on the right hand side, you have only the variable x. You have only x as a variable. You see this? So y is on one side you have only y, and the other side you have all x. So you call this as an explicit function of x. Even in this one, see, even in this one, what do you notice? You notice that, see, on this side you have only y. See, you have only y here, and all those terms in x are on the right hand side. Okay, so whenever you see any function given in the form y equal to f of x, y equal to f of x, it is an explicit function being defined. Okay, so till now in all these videos, in all these lectures, the problems we have differentiated till now, they all were explicit functions, because in every single question you notice that you were given function of x and you wrote it as equal to y. So that was in the form y equal to f of x, and hence those all were explicit functions that you differentiated, you without knowing it. You did not know that those all were explicit functions, but they all were so. So here now we come to implicit functions, which are now, so this type we had been already doing, okay, and we have done enough for here. Now we are going for we have done enough in this. Now we are going for the implicit functions. Okay, so here I define now implicit functions. See here, how do we define implicit functions? I write, if if x and y are real variables, they are real variables such that a function f is defined on x and y. See here what I wrote, a function f is defined on x. You check this. Here I wrote a function f is defined on x. I wrote only x. But here what I'm writing, a function f is defined on, I'm writing a function f is defined on x and y. It is defined on x and y. And we can write f of x comma y equal to 0. And the function is defined on x and y such that we can write f of xy equal to 0. We can write f of xy equal to 0. And when we have anything like this, then what we know, what we say that the function f here is, we say that function f is an implicit function. Okay, then then f is said to be an implicit function. It is said to be an implicit function. Okay, so here what you will notice is, when you have an implicit function defined, remember students that you are not writing y in terms of x. That y in terms of x you wrote only for the explicit function. Y equal to f of x form is for explicit function. For implicit function, you do not have y on one side and x on the other side. Rather, you have x and y both merged together. They are mixed together and the function is defined. I will give you an example for this. Check. See, for example, suppose I have x square plus y square minus 9 equal to 0. So definitely there is a function defined here also. There is definitely a function is defined here. But do you have here y equal to f of x form? No. Do you have here y equal to f of x form? No. Such function is known as, definitely there is a rule. Remember students, whenever there is a rule, there is a function. So can't I say that there is a rule working here? Yes. Okay. When I write, when I write x square plus y square, when I write x square plus y square minus 9 is equal to 0, what is the rule? The rule is sum of square, sum of square of x and square of y is equal to 9. That is the rule. What is the rule? The rule is very simple. What is the rule? Sum of square of x and square of y is equal to 9. That is why 9 minus 9 will be 0. So all those, see, because of this rule, the x and y values are governed. They are always governed. You cannot have, see, in x square plus y square minus 9 equal to 0, you can never have x square equals to 10. You know why? Because if you have x square 10, then y, this equation is not satisfied. This equation is not satisfied. If I have x square only as 10, as you know, y square being a square term, it has to be either 0 or greater than 0. You know, it cannot be negative. Now, if x square is only 10, you check. If I write x square only 10 here, what will happen? The equation will be 10 plus y square minus 9 equal to 0. So it will be y square plus 1 equal to 0. So it will be y square equals to minus 1. So if x square itself is 10, y square will have to be negative 1, which is not possible. Which is not possible. In short, what I'm trying to tell you is that x square plus y square minus 9 equal to 0 also gives us a rule. It is also giving us a rule. And if it is giving us a rule, definitely there is some function over here. And that function is known as implicit function. Why implicit function? Because here I notice that function is in the form, the function is defined on x and y both. See, it is x and y both. Here you see x and y both. The function is in the form f of x comma y equal to 0. Whenever you notice a function which is in the form f of xy 0, it is known as an implicit function. In today's lecture, I will solve few problems, and in lectures to come, you will notice there are plenty of implicit functions that we are going to deal with. Okay, so you may write this definition of implicit and explicit functions. Okay, so here we have few functions that we are going to differentiate, and these functions which we have to differentiate, they are implicit functions. So here in that, we have question number 3 from exercise 1.3, where we have to find dy by dx. They say find dy by dx if x root x plus y root y equals to a root a. So before I start doing what I'm asked to do, let me first tell you that this is an implicit function. This is an implicit function. Now, if you are thinking that how is this implicit function, let me tell you, if I take this constant a root a on the left, if I write this constant a root a on the left, what will happen? It will become x root x plus y root y minus a root a equal to 0. And now what I see? I see this equation gives us a rule in x and y, and that rule is f of xy equals to 0. See what we have? We have a rule defined on x and y. We have a rule here that is defined on x and y. X root x plus y root y minus a root a is 0. So that rule I indicate by letter F. So I can say that this equation, you can check. You can check what we notice. We notice that this equation is in the form f of xy. See, this whole thing is f of xy equal to 0. F of xy, f of xy equals to 0. So hence I call this as an implicit function. Remember students, I do not have here the function defined in the form y equal to f of x. See, I do not have in the form y equal to f of x. In this, what we have, whenever we have in the form y equal to f of x, we have all the expression of x on one side, and on the other side we have only y. Okay, so I hope you have followed that this is an implicit function, and we need to differentiate this to get the value of dy by dx. So how I do it, that you will now have to check. So just be with me for 2 minutes and I'll do that. So this is what I'm given. See, they say find dy by dx if this. So this is actually given to us. So I will write here given. I write here given. What am I given? I'm given x root x plus y root y equals to a root a. And now I write differentiating with respect to x. Differentiating with respect to x. Now, how do I know that I have to differentiate with respect to x? Very simple, because you can check what am I asked to find. I'm asked to find d by dx of y. So since I'm asked to find d by dx of y, I understand that I have to differentiate with respect to x. I have to differentiate with respect to x. You got this? So here we are differentiating with respect to x. So I will get here, therefore, d by dx of x root x plus y root y equals to d by dx of a root a. Okay. So next step, it will be d by dx of x root x. You all know x root x can be written as x into x raised to half. And this will become x raised to 1 into x raised to half. So x raised to 3 by 2. So x into x raised to half is x raised to 3 by 2. So d by dx of x raised to 3 by 2 plus d by dx of the other term, which is y into root y. So d by dx of y raised to 3 by 2 equals to 0. A root a is a constant. Okay, if you have a question in your mind that how do I know that a root a is a constant? Okay, very simple students. Though they haven't said anything about a has to be taken as a constant, because you can check here that we have to find, what we have to find is dy by dx. We have to find dy by dx. So that is, I have to find the derivative of y with respect to x. That is, I have to find the instantaneous rate of change in y with respect to x. So if they haven't said anything about a, from here, I understand only y and x are variables. Only y and x are variables, and a is a constant. So here I take a as a constant, and now what I do next is, see here, now here I have to recognize the function and differentiate. So this is d by dx of x raised to 3 by 2. This is variable raised to constant, and the variable is matching here. See, this variable is x and here also x. It is direct function of x. So the derivative will be 3 by 2 x raised to 3 by 2 minus 1 plus. This function is also variable raised to constant, but what you notice that variable here is y, whereas this variable is x. So this variable is not matching. So this is d by dx of f of x raised to 3 by 2 type. It is d by dx of f of x raised to 3 by 2. So here the derivative will be 3 by 2 y raised to 3 by 2 minus 1 into d by dx of y equals to 0. What you can do is, see, 3 by 2 is here and here both. So you can divide throughout by 3 by 2, and that 3 by 2 is now cancelled. So you can write here dividing throughout the equation by 3 by 2. So we will get therefore x raised to 1 by 2 plus y raised to 1 by 2 dy by dx equals to 0. So we have now this x raised to 1 by 2 is root x. So, and this is root y. So the final answer is dy by dx is equal to minus of root x upon root y. This root x will go there, so you will get minus root x, and then since it is dy by dx is multiplied by this, so this root y will go in the denominator. So dy by dx is negative square root of x upon y. This is final answer. I hope you all have followed this. So enough for this lecture. We will take some more problems in the next lecture, that is lecture number 15 on derivative, and in that we will differentiate few more implicit functions. Thank you.